This next session is a special lecture by Assistant Professor Mate KOVACS titled Types of Machine Learning. First, I would like to provide some brief background on the professor. Mate KOVACS received his PhD in engineering from Ritsumeikan University in 2021. He currently serves as an assistant professor here, where he is responsible for the artificial intelligence and data science classes at the College of Information Science and Engineering. His research interests include natural language processing, data mining, and deep learning for business data analytics and decision support. Of course, he'll be able to explain that far better than I can. We hope this lecture will give you an idea about the courses available at Ritsumeikan University. As I mentioned earlier, he'll be hosting his own Q&A section. So if you have any questions for him, please be sure to get them into the Q&A box during his session where he can respond to them. Professor KOVACS is joining us remotely, as you can probably see right now. Professor KOVACS, can you hear me?
Yes, I can hear you.
Great,
Thank you very much.
How are you doing today?
Yeah, fine. Thank you very much. And thank you very much for the introduction.
Oh, not at all. We're very looking forward to hearing you speak. I'll let you take it from here.
Sure. Thank you. And welcome, welcome, everyone. I'm really glad that so much of you could join today's guest lecture. And as I was introduced, I'm Mate KOVACS from the College of Information Science and Engineering, and I'm currently associated with the eSociety laboratory. So first, let me introduce the eSociety laboratory in a few minutes. Okay. So welcome to the eSociety laboratory. As you can see, besides students, rabbits are also hardworking members of our laboratory. Okay, so the laboratory was actually established in 2014, but that time its name was Global Innovation Laboratory. And there are 3 instructors involved with the lab: Professor Viktor Krisanov, who is the head of the laboratory, Professor Sherdult, who is a professor at both Ritsumeikan University and the University of Zurich, and finally myself, and I joined the lab as an instructor in 2021. At the eSociety laboratory, we deal with social network analysis and its applications, statistical simulation and modeling, natural language processing, machine learning, and other big data-oriented data science projects. Here are just a few examples of the thesis titles from the undergraduate, master's, and doctorate students. For example, an artificial immune system to optimize energy consumption for green manufacturing, or blood bag delivery planning using genetic algorithms, or road surface quality assessment, and the list goes on. Along the years, there were multiple internship students coming from other universities and actually from the industry as well, from many countries, as you can see here. The instructors in our lab are actively participating in reviewing scientific papers and giving guest lectures. As you can see here, our environment at the lab is super international, and we have members from about 15 countries in total. Our graduates work at many countries, including Japan, of course, in companies, for example, JR Central, German Telecom, Suzuki, Toyota, and list goes on. And sometimes we have food parties and other social events as well, where we can learn more about each other's culture. And finally, we love sports and music, and many of us can play an instrument or do some kind of sports. So now let's move into the main topic of today's lecture, which is about types of machine learning. So at Ritsumeikan University, among other classes, I'm responsible for the AI course at ISCC, which is a class for second-year students who already have some experience and familiarity with data science and linear algebra, calculus, and so on. So today's lecture is really just a brief introduction to the field of machine learning and what are the main types of machine learning. Today's agenda is the following. So first, I will talk about what is machine learning exactly and where it is located among other fields. Then I will introduce what basic types of machine learning there are and also talk about deep learning because it's the most prominent methods of machine learning nowadays. And finally, I will outline the summary of today's lecture. And after the lecture, feel free to ask your questions in the Q&A corner. So what is machine learning? One way of looking at it is that machine learning is a subfield of artificial intelligence that focuses on using data to learn potentially meaningful tasks that can benefit humans. But I think to grasp what is machine learning, first is the best to understand what is learning. Nobel Prize winner, economist, and information processing specialist Herbert Alexander Simon said that learning is any process by which a system improves performance from experience. To be more precise, machine learning is a part of artificial intelligence that deals with algorithms that improve their performance at some task with experience. And this tuple actually gives us a well-defined learning task, as we can see here. And practically speaking, it means that we try to program computers to optimize a certain performance criterion using historical example data. And most of machine learning algorithms are using example data to learn from already existing samples to be able to refer to future and unseen data points. So when machine learning is actually useful for us? In general, we can say that it's beneficial when human expertise doesn't exist or is just hard to explain it. Also, there are situations where models must be rebuilt over time or there is just too much data for human manual assessment. Machine learning involves multiple fields and subfields, so it's quite ambiguous where it is located exactly, but we can think of it as a multidisciplinary field of computer science, which is closely related to data science and mathematics. So using methods and techniques from multiple fields, with machine learning, we are trying to recognize or generate data patterns or possibly recognize anomalies and predict some values based on the target task. There are three main types of learning based on how the system learns. So what is the feedback basically? The first one is supervised learning, where input-output pairs are observed and the task is to learn a function that maps an input to an output. We call this a supervisory signal. For example, our task is to recognize pictures of cats and dogs. Then our input will be pictures of cats and dogs, and our output will be the corresponding labels, in this case, a cat or dog. The algorithm learns from these picture label pairs, and it's getting better and better at telling from a picture if it's a dog or a cat, even if that picture wasn't involved in the learning part. The reason why the algorithm is getting better at predictions is that it learns from its own incorrect predictions. The second main type of machine learning is unsupervised learning. In this case, we are learning a model from completely unlabeled data, and we are trying to find patterns in our data. Going back to our cat-dog example, imagine that if we have the same pictures, but these are not labeled, so we don't know which is a cat or a dog. So in unsupervised learning, we try to group the pictures together that are similar to each other, in this case, cats or dogs. The next one is reinforcement learning. Plainly speaking, reinforcement learning is about an intelligent agent taking actions in an environment to maximize a reward. So instead of the input-output pairs we saw in supervised learning, we are trying to correct or suboptimal actions based on how small or big reward we get from our action. It's kind of a trial and error thing, so pretty similar to some human tasks. An example would be to make a machine how to learn how to play chess or a computer game. Now let's dive a little bit deeper into these different types of learnings to understand them better. So putting it into simple terms, with supervised learning, we are learning a model from labeled data. But what this means exactly? So we are trying to learn a function that maps an input to an output based on example input-output pairs. The input is a vector, while we call the output the supervisory signal. And our goal is to determine the output for unseen examples that wasn't part of the learning process. Supervised learning can involve classification or regression. Classification is about predicting the label of unseen examples. For example, something is true or false, or based on pictures, is it a cat or a dog, or based on natural text, how the writer feels, negative, neutral, or positive. And on the other hand, regression tasks are about predicting a real valued number. So for example, if we are trying to forecast the sales for a particular restaurant, that's not a label and not a class. We are still learning from historical data, but we are trying to predict an actual number. In this case, we are trying to minimize our error of predicted number compared to the actual sales data. And practical examples of supervised learning from research and the industry can be face recognition or other authentication systems, or sentiment analysis of online customer reviews to learn about what customers think about certain products. The data which is used to create machine learning models are usually divided into 2 or 3 mutually exclusive subsets, as these are used in different stages of building models. When we are talking about learning, we usually mean the training phase that corresponds to the training data set. And in conventional scenarios, around 70% of our original data set is used for this purpose. After we finished learning and our model is trained, we test and validate our model on a smaller subset of the original data set that was not involved in the training process, so we can evaluate our model in an unbiased manner. And if we have enough data points in the original data set, we perform testing one more time on a subset of the original data set that was not part of the validation data. But however, this is not performed in all cases, especially in research, and it's more common in the industry where deploying the models have serious financial consequences and companies have means to accumulate more and more data. Okay, now let's move to unsupervised learning. In this case, there is no supervisory signal or label involved, and we are trying to make clusters of similar data points. We can say our goal is to find previously unknown patterns in a data set, but without pre-existing labels. There are multiple applications of unsupervised learning, such as dimensionality reduction, pattern and feature recognition, data quality assessment, or for exploratory analysis, where we have huge amounts of data, but we don't have labels for it. Now, it might sound really good that we don't really need labels, but actually we don't always get the desired results with unsupervised learning, and the groups we discover might not be fully interpretable for humans. And some practical examples of unsupervised learning from the research community and the industry are applying natural language clustering methods to discover hidden semantic structures over large linguistic data, or generating images or videos, or even synthesizing speech. Now for reinforcement learning. First, let's consider the problem of learning how to play chess. If we formulate the problem for supervised learning, the input is a board position and the output is a move. And considering how many board positions are possible, supervised learning is not really feasible in this case, at least for obtaining satisfactory results. So a possible solution is to choose the best possible action in every certain situation. In reinforcement learning, an agent interacts with its environment and receives rewards or so-called reinforcements from it. The goal is to maximize the rewards at each time step. And instead of the conventional input-output pairs we talked about for supervised learning, here we are correcting or suboptimal actions. This means that unlike in the case of supervised learning, it needs to learn from direct experience. So in case of the chess playing example, the machine needs to play thousands and thousands of games and learn from the rewards. And this reward can be a better table position or just simply winning the game. And actually, the learning how to play chess is a good example when making the reward signal is easier than making a huge label data set for supervised learning purposes. There are multiple fields where reinforcement learning is used, for example, robotics, time series forecasting, and chess or other strategic and logical table games where machine already actually exceeds human performance. So just a quick recap on the differences and the similarities with the three main types of learning. In case of supervised learning, our input is labeled data, so pairs of input and output examples. Our output is the predicted class or value that we basically learning from our incorrect predictions. For unsupervised learning, our input is unlabeled data, so we do not have input-output pairs, and our output will be clusters, so we are grouping data based on similarity. Now, for reinforcement learning, our inputs are states and actions, and we are learning from rewards, which are coming from the given environment to produce actions as outputs. Moving into deep learning, I'm sure a lot of you already heard or even have some knowledge about deep learning, as it is the most popular field of machine learning nowadays. Deep learning can be supervised or unsupervised or even reinforcement. It involves using neural networks, which is just an umbrella term for algorithms that are inspired by the structure and function of actual neurons in the brain. However, this is just a metaphor, and there are only abstract similarities of neural networks with the human brain. The basic structure of a neural network is the following. So we have an input layer for our inputs. We have one or more several hidden layers where the actual learning takes place. And there is the output layer that will produce our actual predictions. The circles here represent individual neurons that are not connected with each other in the same layer, but these are connected with other neurons from different layers. This diagram just depicts a so-called dense or fully connected neural network because every input in a layer has a link with other neurons in different layers in some form. And going back to, again, to our cat or dog classification example, the input layer would involve some kind of matrix representation of our pictures, for example, the color values of the pictures, and different layers would learn different features from the pictures to differentiate between cats and dogs. And simply speaking, with more layers and more neurons, we can learn more and detailed features from our pictures, potentially resulting in better prediction performance. We call a network deep if it involves more than one hidden layers. And in fact, in some cases, there are dozens of these layers in a network to learn more and more about our input data. So I will continue with explaining why would we use deep learning over other machine learning methods. So with conventional machine learning algorithms, we often have to perform extensive feature engineering, which means creating new features manually or with other algorithms and heuristics. However, deep learning is capable of feature learning, which means it can often learn the features by itself from raw data, and we don't need too much feature engineering, or a lot of times actually none. And this obviously minimizes human intervention that can be often biased and can learn features at multiple levels of abstraction that not necessarily mean anything to humans, but important for the network to obtain rich representations of the input data. Of course, not in all cases and studies, but deep learning delivers state-of-the-art performance in multiple fields, such as natural language processing, computer vision, customer need assessment, business management, social and medical sciences, and so on. And here I only introduced one architecture of neural networks, that is the so-called fully connected network, but there are in fact several other architectures. And while one is more useful for example, processing natural language text, other architecture can be more beneficial for dealing with visual inputs, for example, like pictures. The so-called deepfakes we hear in the news are also created with a specific architecture of neural networks that obviously can be beneficial as well, and people use it for actually useful and not malicious tasks. One of the limitations of deep learning is the data dependency. Actually, in a lot of cases, conventional and older machine learning methods work better with small amounts of data. And depending on the purpose of the research or application, another issue could be the black box problem. This means that we don't really know what's going on in the hidden layers of the network. And even if we extract the outputs of internal layers, what we get doesn't really make too much sense for us. So this means that even if a deep learning network is successful at some task, most of the time we don't really know exactly why, because the features it's using are not the same as our perception works. Also, depending on the deep learning model in question, it might require a lot of computing power, and training on the CPU wouldn't be really feasible, especially because finding good parameters for neural networks might take several runs. And nowadays, deep learning networks are trained on graphical processing unit, or GPU. And in the case of the state-of-the-art models, a lot of times they don't even fit into only one GPU and can require days and weeks to build the models. Fortunately, there are cloud-based services as well, where one can rent and use GPU clusters. Now, just to summarize today's lecture, machine learning algorithms improve their performance with experience that usually comes from historical data. There are three main types of machine learning. Supervised learning is when we have labeled data and we are trying to learn from input-output pairs. Unsupervised learning is when we are trying to group unlabeled data into meaningful clusters according to some similarity criteria. And reinforcement learning is when we are trying to make the most optimal actions in a given environment to maximize a reward. Now, deep learning is a subfield of machine learning concerning with neural networks with multiple hidden layers. Although deep learning usually achieves state-of-the-art performance, it's not without limitations. For example, the mentioned data dependency. Okay, this concludes the lecture part, and thank you all for your attention. Now, if you have any questions regarding this quick introduction to the types of machine learning, or just about machine learning or deep learning in general, I would be happy to answer. And please use the Q&A sections. Okay. So which language is mostly spoken at your lab? Is it English? And do you have to understand Japanese? In the eSociety laboratory, the language is English. We don't use Japanese. I mean, Japanese students, of course, they can use Japanese among themselves, but we use English, and seminars and everything. And in the ISCC course, the classes are taught in English as well. So you don't have to know Japanese. Okay. Deep learning helps in creating lots of features. Can we create apps with it? Actually, it's few years ago, I would have said that this is really far-fetched, but not anymore, because of models like GPT-3, which can already even you can create simple games with it from natural language input. And this is the same model which is used in the famous DALL-E application, which creates images from text. So actually, yes, it is possible already. Can we find any solutions for black box problems? So most of the time, this black box problem is not really, they don't really care about in the industry. This is mostly about research. Why? Because in the industry, things just have to work. That's it. But in research, a lot of times we want to know why those things are happening. Okay, the prediction performance is really good, but why? What were the features which helped with us, with the prediction? So that's why sometimes it can create problems. Yes. And solutions for it, well, this is really technical, but there is something called feature permutation importance, where you can permute the values of the features one by one and eliminate the features which were not important for the prediction. So is deep learning very CPU and GPU demanding? So if you only use the CPU, yes. If you use the GPU, it's only GPU demanding and not CPU demanding. Basically, if you feed the model to your GPU memory, and everything will be calculated, the matrix multiplications on the GPU, then the CPU actually for the whole learning, you need like 2 threads. So like 1 core is enough. Where CPU actually have a part in data science is pre-processing, because most of the pre-processing is done on the CPU. Do we use the same programming language for all these learning? If yes, which one? Okay, so the programming language in the industry, it can be really case specific. Most of the time, they use Python for the prototype, and actually nowadays, even for the final product, they might only use Python. But that being said, there are cases when the final product have to be written in Java, for example. If you mean that in the laboratory or in ISCC, we don't have a requirement, for example, for graduate research, But for data science and machine learning, Python is really easy to use and recommended. Does Ritsumeikan provide minor in this subject? In this subject, well, if you are in a different course, maybe you're able to take AI, if you mean that, but it's not involved in a major or minor scheme. Which type of learning is the hidden layer for deep learning? So just going back on our slides here, the purple circles are the hidden layers. So after your input, the input vectors are processed by the input layer. They go to the hidden layers where the actual learning takes place. And you can think of it as all these columns of circles, they extract different features from your data. You can think of it this way. Let's say one of them extracts the shadows, one of them different kind of colors in connection, and so on. Of course, this is like the human perception of things and doesn't necessarily work like that, but this is the main idea. And unfortunately, looks like we are out of time now. Thank you very much for all your questions, and I'm sorry that I couldn't answer all of them. And I hope that all of you learned something new today. I wish you luck with your future studies. And thank you very much again for your attention.